functions, and I'm going to give you the basics of it. This is an abbreviated form of the lecture I gave in class. Alright, so let's start with notation. Just like any other function, the inverse function is noted with a little exponent of -1. So sine inverse, cosine inverse, tangent inverse of x, cosecant, secant, and cotangent of x. Now we're not going to be dealing with these, okay? These are just pointing them out so you know they exist. Sine, cosine, and tangent is where we're going to be working on. All right, so let's take a look here. Now, remember from our earlier discussion of functions and their inverses, for a function to have an inverse, it has to be 1-to-1. And a function is 1-to-1 if it passes the horizontal line test. Trig functions are cyclic. They repeat forever and ever and ever, so they're not 1-to-1. In fact, they're very not 1-to-1. They're 1-to-many. So, in order for us to have an inverse of something like the sine of x, which has that nice little up-down motion there, we have to restrict the domain. So the domain we're going to use for the inverse sine is -pi/2 to pi/2. And if you look at the red part of this graph here, all right, that is outlining the part of the sine curve that we're interested in. All right, so -pi/2 to pi/2 on the unit circle is the first and the fourth quadrant. All right, for cosine, again, it's not 1-to-1, it's 1-to-many because it's cyclic. So we need to restrict the domain, and because cosine is shifted 90 degrees from sine, we're going to shift the domain 90 degrees, and we're going to look at 0 to pi. Alright, again, the red part of the curve is all that I'm interested in here. And on the unit circle, 0 to pi is quadrants 1 and 2. For tangent, now tangent's a little different because tangent is actually 1-to-1 for one cycle, right? Remember, tangent has a period of pi, and the cycle that we looked at to describe the tangent curve was -pi/2 to pi/2. That is actually 1-to-1, so I don't have to restrict anything other than to say I'm looking at one cycle of tangent. And again, on the unit circle, -pi/2 to pi/2 is in the first and fourth quadrants. All right, so now, all right, let's look at what the inverse trig functions represent. I'm going to use sine as my example here, but this applies to inverse cosine, inverse tangent, and so on. Okay. All right, so when you look at the sine function right here, right, x is an angle. It takes sine of an angle. So if I reverse this, x is sine inverse of y, right? That's what we would do to turn it into an inverse. Then x is still an angle, right? That hasn't changed. So when I look at this as a function, and I look at y equals sine inverse of x, sine inverse of x is an angle. All right, with that established, if I want to find the sine inverse of -1/2, all right, what am I actually doing here? Well, I'm saying some angle, and I'll change over to theta now because we're more used to seeing that as an angle. We're saying some angle theta, whatever, some angle theta is sine inverse of -1/2. All right, so again, if I reverse my notation, that means that sine of theta, I don't know why my thetas are coming out so bad, is -1/2. Now we've solved problems like this before, right? You go over here to the unit circle, and you say, well, first of all, sine theta is negative, so where is sine negative? Well, sine is negative in the third and the fourth quadrants, but the domain for sine inverse restricts us to first and fourth, which means the angle that I'm looking for is down here in the fourth quadrant. And then I just need to know where is sine equal to 1/2, and that is pi over 3. So pi over 3 on this side is going to be negative pi over 3. Now notice I didn't say 7 pi over 3. Okay? That's right, right? 7 pi over 3. Because I have to remember when I'm measuring negatively, I'm measuring in this direction. Alright, so when I say negative pi over 2, I'm measuring this way. Alright, so this becomes the angle that I'm looking for as opposed to going all the way around that way. Alright, so that means that theta equals negative pi over 3. Actually, it's pi over 6, isn't it? Sorry, pi over 6. Negative pi over 6. Alright. Okay, so what else can we do with this? Composing functions. Right? If I need to compose a function with its inverse, I know from algebra that when I compose a function with its inverse, I get the x out. Right? Same thing this way. What I have to be careful of is when I do that here, I have restricted domains that I'm dealing with. So if I want to take the inverse sine of pi over 8, I have to know that pi over 8 is in the right spot, right? Because the domain, again, for inverse sine is negative pi over 2 to pi over 2. So the angle, in order for me to say that this is equal to pi over 8, I need to know that that angle lies in either the first or the fourth quadrant. And pi over 8 does. It's in here. Okay. So as long as the angle that I'm dealing with falls within the domain of the inverse sine, I'm okay. So I can say that's equal to pi over 8. Over here, okay, over here I have a little bit of a problem because 5 pi over 8, that's actually 5 over 8 is more than a half, which means 5 pi over 8 is over here. And 5 pi over 8 is now outside the domain of the inverse sine. Because it's outside the domain of the inverse sine, I have to do a little bit of busy work here. Okay. Alright, so in this quadrant, the sign is positive, right? So I have to pick whichever of these two quadrants the sign is positive in. Alright, so I'm going over here. Alright, which means, again, I'm looking at pi over 8. Alright, so when I take the sine inverse of the sine of 5 pi over 8, I'm not getting 5 pi over 8. I'm getting pi over 8. Alright, so anytime you have to compose a trig function with its inverse, with its own inverse, you have to check the angle and make sure it falls within the correct domain. Okay. Alright, what's next? Alright, what if I'm composing two different trig functions? Well, I can step through this, right? Tan inverse of 1/2. Remember, inverse trig functions are angles. I take the sine of an angle. So the first thing I'm going to do is let theta, the angle, equal tan inverse of 1/2. Then tangent of theta equals 1/2. Now that is not a unit circle value. There is no place on the unit circle where the tangent is equal to 1/2. So what that means is I have to do a little bit of work over here. So if I come over here, 1/2 is positive. That means the tangent of theta is positive. Tangent is restricted to the first and fourth quadrant, and it's positive in the first and negative in the fourth. So I have a triangle. And here's my theta. Alright, so tangent is opposite over adjacent. And if you use the Pythagorean identity, right, 1 squared plus 2 squared equals the hypotenuse squared. I'll call that h. Alright, so that's 1 plus 4, so that's 5. So that means h equals the square root of 5. Alright, now we said tan inverse was theta, so what am I actually looking at here? I'm looking at sine theta. And I can read that off the triangle now. Sine is opposite over hypotenuse. So opposite over hypotenuse. And then just rationalize that, because I know the online homework system wants rationalized answers, not square roots in denominators. Alright? Again, that process will work anytime you're composing two trig functions, two different functions with their inverses. Okay, I just noticed a mistake that I made. Where is it? Back here. I want to fix it before I close out the video. This isn't pi over 8. It's actually 3 pi over 8. Okay. No, that's not right. That's right. There we go. 3 pi over 8. Let me explain why that is. I'm looking at basically this as my reference angle. So if I take pi minus 5 pi over 8, I'll get the reference angle in the first quadrant. Alright, and that is 8 pi over 8, right, to get a common denominator. So that's going to give me 3 pi over 8. Alright, sorry about that. I don't want to have to go back and edit the video. Alright, so that should be 3 pi over 8 there. Alright, hopefully there are no other glitches. I know this went fast. I managed to cover in 12 minutes what I covered in an hour and a half in class. So this should be enough to get you through the online homework. And we'll talk again on Tuesday.